So we have been given a set A which contains the elements 1, 2, 3, 4, 5, and we have been given two relations R and S. So R consists of the pairs 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, 3, 4, 4, 3, 4, 4, 5, 5. S contains the pairs 1, 1, 2, 2, 3, 3, 4, 4, 4, 5, 5, 4, 5, 5. Now, R and S are equivalence relations. We can verify that. R contains all the reflexive pairs 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. R contains all the symmetric pairs. So because 1, 2 is there, its symmetric pair 2, 1 is there. 3, 4 is there, its symmetric pair 4, 3 is also there. S contains again all the reflexive pairs 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And it contains 4, 5 and its symmetric pair that is 5, 4. So now we can we have to find the partition induced by the smallest equivalence relation which includes both R and S. So few things that we'll systematically discuss over here. First thing that we have studied is if you have a partition of A, it can induce an equivalence relation. So inducing equivalence relation or finding an equivalence relation, producing an equivalence relation from partition, we have studied that. Producing a partition or finding the partition induced by an equivalence relation is also what we have discussed. In that case, we first find the equivalence classes and then we put those elements together which have the same equivalence classes. We put them together as the different compartments within the partition. So that is what we have already studied. Now here, when they say a smallest equivalence relation containing both R and S, R and S. So will intersection work here? Intersection will take the common pairs which are there in R as well as S. But there will be some pairs from R and some pairs from S which will be excluded, right? So that is not what we want. We want to include all the pairs from R and include all the pairs from S. That means it is asking us to find the union of R and S. Okay, so find R union S. Now, when you find R union S, okay, what we'll do is we'll do it both the ways. First way we'll do it is the traditional way. We'll first find R union S. We'll make sure that it is reflexive, symmetric, and transitive. And therefore, the smallest equivalence relation will also be found out from that. And then we will find the partition induced by the equivalence relation. Okay, so going by this route, first R union S. Now let's just list down what R union S looks like. Okay, so R union S will contain 1, 1. It will contain 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. It's there in both. And from R, it will contain 1, 2, 2, 1. And similarly, we'll also include 3, 4, 4, 3. From S, will include 4, 5, 5, 4. Okay. Now, firstly, by observation, you can see that all the reflexive pairs are there. But still, let's draw it as a matrix. Okay. So in matrix, you can first draw the entire diagonal. We'll need a 5 by 5 matrix. All the diagonal elements are ones. That is a starting point. We can say 1, 2, and 2, 1 is there. We'll mark that. 3, 4, and 4, 3 is there. We'll mark that. 4, 5, and 5, 4 is there. We'll mark that. Okay. Now, by observation of this matrix itself, you can say that this is the matrix of R union S. And you can say that it is already reflexive. All diagonal elements are 1. And R union S is also already symmetric because the matrix is also symmetric. And by observation, you can say that all the symmetric pairs are there. So if you take R union S, automatically it is reflexive as well as symmetric. And fun fact, if you take R intersection S, that is not asked in this question, but if you take R intersection S, it is automatically equivalence. But when R and S are both equivalence, their intersection will be an equivalence. But in case of union, when R and S are equivalence relations, their union need not be an equivalence relation. So reflexivity and symmetry is not what we have to worry about. We have to worry about the transitivity. So how to make it transitive. Okay, we can check whether it is transitive or not, but let's not waste time in that. In the previous video, you have already studied how to find transitive closure using Warshells. You have the matrix in front of you. Let's examine it row by row, like a row and column. So let's examine one by one as we have studied in transitive closure. So first row and first column, if we highlight that, and if we find wherever there is one and their intersection, okay. So as you can see, already there is one over there, nothing new to be added. Next, the second row and second column. As you can see, wherever there is a 1 in the second row and second column, there is already a 1 at their intersection. Then let's highlight the third row and the third column. Again, you can see that wherever there is a 1 in the third row and third column, there is already, right, there is already a 1 at their intersection. So nothing new added uh, in this iteration as well. In the next iteration, let's take the fourth row and the fourth column. So in this case, you see that now here, um, 3, 3 comma 5 will become 1 and 5 comma 3 will become 1. Okay, because of these two ones. And ultimately, let's go to the fifth row and fifth column. Nothing new to be added over here. So we are good, right? We have found a transitive closure. We added the pair 3 comma 5, 5 comma 3. So now, if you see this matrix, okay, from this we can go back and write the relation. Okay, the exact original relation of R union is only one extra pair is added, that is 3 comma 5 and 5 comma 3. Now we'll find the equivalence classes. So the equivalence classes will give us the partitions. So equivalence class of 1 consists of 2, and equivalence class of 1 consists of 1 and 2. Equivalence class of 2 consists of again 1 and 2. Equivalence classes of 3, 4 and 5 contain 3, 4 and 5. So therefore you can say that the compartments are 1, 2 and 3, 4, 5. So the partition is 1, 2 in one compartment and 3, 4, 5 in the other compartment. We can go other way around as well. Okay, so we can see that the partition, okay, we have R and S. So let's go the alternative route. Here we first found the equivalence relation and then found the partition going backwards. Now let's do this. Let's find the partition first and then find the equivalence relation induced by the partition. Okay, so in that case, firstly what we'll do is we'll observe the partition of A induced by R. What is the partition of A induced by R? So as you can see, the even by observation, as you can see, 1 and 2 are in one compartment and 3, 4, 5 are in the other compartment. Right? Sorry, 3 and 4 is in one. So 1, 2 is in one compartment, 3, 4 is in another compartment, and 5 is in its own separate compartment. So there are three compartments in this partition. Now there is a trick that we can do over here, or a step that we can do here. Indicate this by an undirected graph. Okay, so 1 comma 2 is in one compartment, so we'll draw 1 and 2 as nodes and connect them with an edge. Okay, 3 and 4 are in one compartment, so we'll draw 3 and 4 and connect them by one edge, and 5 is a separate node. Now if you consider this graph 1, 2, 3, 4 and 5, you can say that it contains vertices V, it contains the edges, it is a graph, right? It is a graph, but it is not a connected graph, right? So if you start from 1, you can go to 2, but if you start from 1, you cannot go to 3. Similarly, if you start from 3, you cannot go to either 1 or 2. If you start from 5, you can go nowhere else. So it's an isolated kind of a vertex. So this is a disconnected graph. But in such a graph, there is one interesting thing that we can find out. What are the connected components? So what are the components or the subgraphs of this graph such that if you start at one node, you can reach all other nodes within that subgraph or within that connected component. So in simple words, if you see, observe this graph, if you start at 1, you can reach 2. If you start at 2, you can reach 1. If you start at 3, you can reach 4. From 4, you can reach 3. So 1 and 2 is in its own connected component. 3, 4 is its own connected component. And 5 is an isolated vertex. Okay. Now, similarly, for the partition of A induced by S, here you can see that 1, 2, and 3 are in their own compartments, and 4 and 5, they will be in a separate compartment. Again, graphically, if you denote this, 1, 2, and 3 are isolated vertices, and there is an edge between 4 and 5. Now, when we are taking union of this, we simply combine both the graphs. So what do? We simply combine the edges in both the graphs. So from the first graph, we have the edge 1, 2, 3, 4, and from the second graph, we have the edge 4, 5. So when we are saying combined graph, it will contain the edges 1, 2, and 3, 4, 4, 5. Okay. Now, what are the connected components in this new graph that we have drawn? From 1 you can reach 2, from 2 you can reach 1, from 3 you can reach 4, 5, from 4 you can reach 3, 5, from 5 you can reach 3, 4, but from either of 3, 4, 5 you can reach neither 1 nor 2. Similarly, from either of 1 or 2 you can reach neither of 3, 4, or 5. So therefore 1 and 2 is a connected component, 3, 4, 5 is a connected component, and that is the answer. So that is the partition of, so that is your partial answer, you can say. The partition induced by R union S on the set A is consisting of these two compartments, these two connected components, that is 1, 2, and 3, 4, 5. Understood? And now from this, we'll find the equivalence relation. So 1, 2, connect them in all possible ways, or make pairs, relate them in all possible ways. So 1, 2 will result in 1, 1, 2, 2, 1, 2, 2, 1. 3, 4, 5 will result in 3, 3, 4, 4, 5, 5. 3, 4, 4, 3, 4, 5, 5, 4, and 3, 5, 5, 3. That is our answer. Okay, so this is an alternative way, alternative route to find the answer. Okay. If you have any questions, any doubts, do post them in the comments below. This was smallest equivalence relation. Okay. In general, for any smallest equivalence relation on uh, a set A, like if you are given any relation, you simply have to find its reflexive, symmetric, and transitive closure. If you are given two relations and you are asked to find a smallest equivalence relation containing both the relations, you take their union and you can go by either of these ways unless it is specifically mentioned in the question. Okay, so that's it. If you have any doubts, do post them.